Hello, and welcome to another episode of the Geotechnical Engineering Podcast, a podcast focused on helping geotechnical engineers stay up to date with technical trends in the field. I'm your host, Jared Green, and I've practiced as a geotechnical engineer for over 18 years. And in addition to practicing engineering, I enjoy mentoring young engineers and first-generation college students. I've focused on helping to increase the number of pre-college students that are interested in STEAM majors and fields. By STEAM, that's science, technology, engineering, art, and mathematics. In this episode of the Geotechnical Engineering Podcast, I'll be talking with Tony Amos, the Senior Vice President at GI Energy US and a recognized expert in multi-renewable solutions involving energy foundations and ground source heating and cooling solutions. We'll be talking about energy piles and more specifically about ground sourced heating and cooling solutions. Tony has been a key player within the GI Energy UK organization between the years of 2008 and 2017, and now Endurant Energy, previously known as GI Energy US. He's involved with raising the profile of all ground-sourced heating and cooling solutions, both in the UK and internationally, and at the same time continuing research into the effects on foundations with Cambridge University, Virginia State University, Boulder University, and Texas A&M University. He actively oversaw over 50 high-profile energy pile projects in the UK. During 2017 and 2018, he worked with a world-renowned technology client in California on installing one of the largest energy foundation projects in the world at their new Mountain View campus. He has worked with many universities across the US, assisting them in their pursuit of achieving a carbon zero campus. Most notably is Michigan State University, where they provided a high-level review outlining a district energy geothermal solution that will enable them to meet their carbon reduction goals of 60% by the year 2040. He is currently involved on a groundbreaking all-electric office project in New York City that utilizes a ground-sourced solution using energy foundations to deliver 30% of the building's heating and cooling, with the remainder coming from an air source heat pump. And with that, let's jump right into our conversation with Tony Amos. Tony, welcome to the Geotechnical Engineering Podcast. How are you doing?
Thank you, Jared. I'm doing fantastic. Thank you very much.
Excellent. I'm doing well. I've really been looking forward to this conversation, so I'm glad that you could carve out some time for us. It's going to be awesome. All right. So question for you. I already introduced you to our listeners, but if we said in your own words, can you tell our listeners a little bit more about your career path and also a little bit more about what you do at GI Energy?
Sure. So I remember being at school, doing my O-levels, as they called in the UK, and never really sure what I wanted to do as a career until a guy from a local college came into the school and started talking about civil engineering, building and civil engineering. And what really got me infused was, the talk about, building big things, dams, airports and bridges and things like that. And from that moment in my life, I realized that construction was where I wanted to head. Academically, I wasn't the brightest at school. I was more hands-on. So I went to college and I did a building and civil engineering diploma, ordinary level, higher level at a university in London. And then I started with a construction company working in an oil refinery as a setting out engineer. I've got some good tales of things that went badly wrong for me setting it out. But I moved, and that was down in an oil refinery in Southampton. And then I moved to London, where I was working on a deep basement project. Probably my first real heavy geotechnical experience. For the British Library. It had 5-6 basements, and it was a top-down construction process, which was really interesting. And it was at that time where everyone was looking around. There's a boom in the construction industry, And I ended up leaving that company and joining a company called Cementation, which specialized in foundations. Never really kind of sort of thought much about it, but I came up against some real inspirational people at Semos. Guys like Ken Fleming and David Greenwood, Rab Fernie. In the UK and internationally, they're pretty world famous guys, world leading experts in stuff, especially Ken Fleming for me, David Greenwood in chemical grouting, and I got involved in all these kinds of projects these guys were involved with. And I spent probably 15, 20 years of my life with Cementation, and it became Cementation Skanska in the UK. I moved to Hong Kong, did 6 years in Hong Kong with the Cementation team, helping them set up the diaphragm walling team in Hong Kong. And in Hong Kong, I project managed some really enormous projects. I actually left the UK in the depths of recession and moved to Hong Kong in 1995, 2 years prior to the handover, to an absolute construction fest. There were suspension bridges being built everywhere. There was the new airport being built.
Wow.
And I was looking after some phenomenal sized projects. And it was just very, very eye-opening. The scale of some of the projects that were going on out there. And my two daughters were born in Hong Kong, and kind of after probably a year, 2 years, decided it was time to head back to the UK in 2000, and rejoined the foundations team in the UK. And it was Rab Fernie suggested to me that maybe I would like to look at this energy foundation solution. And so I grabbed hold of it. I was the champion within the Cementation Skanska, as they were then called, and that's kind of where it all became. I went geothermal, and I thought, this is such a no-brainer solution. I'd seen geothermal works going on, drilling purpose-made boreholes down to 500 or 600 feet, one borehole a day. I'm thinking, well, why can't we put geothermal loops into these building foundations? And I came across, and I did a joint study with a guy called Duncan Nicholson at Arups. And together we really raised the profile of energy foundations. and that's kind of where it all started for me. Coupled with the fact I was closing in on a midlife crisis, I think, and I've done 25 years in drilling holes and filling them with concrete. And I kind of, it was a good stepping stone into something that I suddenly thought, well, I'm doing my bit to save the planet, and environmental issues were becoming more and more prevalent in society. And I was very proud to say, well, look, this is a renewable energy solution, and we need to be moving in this direction. And so for the last 20 years of my life, and I'm actually shocked to say that, I've been trying to raise the profile of geothermal solutions, but predominantly my main driver has been, let's use the building foundations that are being installed to provide a significant proportion of the building's heating and cooling. It really is a no-brainer, especially if the foundations are deep enough and the building height isn't too tall. It makes for a great solution. And so pretty much that's how I got involved. I ended up leaving Cementation because what happened was, what I realized was, and this is something I'm going to mention later on, is that this is where geotechnical meets mechanical, and the two need to come together quite significantly, because this is a geotechnical and a mechanical solution. So I call it a geomechanical solution, because the two items are so connected to one another that it should never be designed. The ground loops should never be designed by one party, and then the mechanical system by another party. The two systems need to be talking to one another, and it is so important. I've seen so many projects over the last 20 years that have gone badly wrong because people don't connect with one another. And so yeah, so I joined GI Energy in 2007, 8, and a couple of guys, Mike Wysocki from Thatcher, gave us a call in the UK and said, "Look, we really like what you guys are doing. You know, can we be part of what you do?" And then the next thing I know, I'm on a plane out to Chicago,
Okay.
meeting some pretty inspirational guys in the US, and that's kind of where it all started, 2010, 2011. And yeah, so it's you know, I feel, like I said, I feel like I'm doing my part to try and save the planet. What's going on? So it's it's been an exciting last 20 years of my life for sure, and only now are we really seeing some maybe takeoff here in the US for the type of solutions that we're trying to drive here.
I love it. It's great to see, I think for me, just to see the progression, because honestly, you're talking about your career path, and it sounds like multiple different careers there, and it seems like when you see the thread that kind of connects them all, it's solving problems, and then you also have this sustainability bent, which is interesting because we talked to a lot of folks about geotechnical engineering, and there's obviously a lot of overlap with, say, environmental engineering, or within, traditional site civil engineering, which falls under the umbrella of civil engineering. We also hear about a lot of overlap with structural engineering, but we don't typically hear people talk about the overlap with the mechanical, electrical, plumbing. But with the geothermal and the ground, the ground couple, that you guys have to talk together. Otherwise, you're going to have serious issues in the long run. So
Absolutely.
that's impressive. And you know, as far as how you get into ground source heating and cooling solutions, I mean, do you find that you were going back to what you learned in school, or was this a lot of learning on the ground?
So there's a funny story, because one of my worst subjects at college, university, was fluid mechanics.
Look at that.
I actually had to retake fluid mechanics, and so yeah, that's kind of come back to me. But again, and again, this is one of the questions you're going to ask me a bit later on. Is it's recognizing, and it's important to understand where you perform best. I did an MSc in construction project management in Hong Kong, and one of the things I learned there was that construction good project management is the art of achieving objectives through the actions of others.
Okay.
And when you look at some of the projects that you end up working on, some of the really enormous projects I work on, you've got to rely on other people to deliver as well. And again, it comes back to good planning. The devil is in the detail, but that plan, you need to be constantly checking, against what you plan for, make sure you're delivering on time and things like that. But yeah, it's a great, the construction is a great place to be for sure. So
I think in order to truly, appreciate, the geothermal solution as an energy foundation, it would be helpful if you could just walk us through geothermal as a whole. You could stay high level if you want to, but just walk it through, geothermal. Like, what is the ground couple?
Yeah, so sure. So very simply, I mean, all we're looking to do is to exchange heat with the ground, and we do that by placing geothermal loops into the ground. Over the last 20, 30 years, and in fact, the US was pretty a big driver of geothermal, and then it kind of lost its way a bit when cheap gas came along. But in essence, all we're looking to do is pass geothermal loops through the ground. The ground will be, once you go below probably 10 feet, the Earth's temperature is pretty constant, between 50 and 60 degrees Fahrenheit. And all we're looking to do is to exchange probably 10 degrees of heat with the ground. So in wintertime, we would circulate fluid running into the ground, probably 10 degrees, 20 degrees cooler than is the ground. So when the loops come back into the building, they've been warmed up by that Earth's temperature. And that small temperature difference, we can then pass that through a refrigeration cycle. It warms the liquid refrigerant up by that 10 degrees Fahrenheit, that then pushes it to its boiling point. It's then compressed and converts into a vapor. This goes back to my fluid mechanics.
There you go.
But and so you're then transferring, that low grade heat into about 130, 140 degrees Fahrenheit into the building, and you're delivering heating in a very efficient way. And similarly, in the summertime, you operate the system in reverse, and you can provide a cooling solution to the building. And because the ground is at between 50 and 60 degrees Fahrenheit, you can then deliver cooling to the building very efficiently. So we talk about COPs, coefficients of performance. So conventional gas-fired boiler. So for every 1 unit of gas that you burn, you only get about 0.8 units of heat out of it. But with a ground source heat pump system, for every 1 unit of electricity or energy that you use to create heat, you can deliver 4 units of heat. And in cooling, it's 6 units of cooling. So it's kind of, and you can see the difference then. It's that difference that is where the real energy savings are of this type of system. So it's basically fridge technology, exactly the same as the fridge in your house.
Wow, look at that.
Exactly the same methods. You bring your groceries home, you put them in the fridge. The heat is taken out of the fridge, and that's dissipated by the kind of all that piping at the back of your fridge. That piping we put in the ground. So it's very, very similar technology, and it's a pretty straightforward solution. The key to it is understanding the building itself that you're heating and cooling, and developing an energy model in a lot more detail. And what's been traditional for the past, ever since I've been involved, is a mechanical engineer will work out what the peak heating and peak cooling is for his building, and all they simply do is and this is probably doing an injustice to some of the mechanical engineers, so I apologize to any of those guys listening. So this is geotechnical, so we were right, we can talk about them.
Exactly.
But what they'll do in a heating situation is they'll probably double the peak load, and then they've got their gas-fired boiler size, and that's it. What we try and do is we look at every single hour through the year, 8,760 hours a year, and we will look at actually how much heating is needed, how much cooling is needed, and then we can then develop the system in that way. And so when you're heating and cooling at the same time in some of these commercial buildings, residential buildings, we can take heat from a cooling process and transfer that into other parts of the building that need the heating. And when you do that, you're not then rejecting heat to the atmosphere. You're recycling and reusing, and that's the real component that we as a business hone in on, and we try and capitalize on that, because that's where the real energy savings come from, in addition to the savings that I mentioned previously.
Got it. So getting the system as efficient as possible, so you're not losing anything. You're using whatever you're bringing up or putting back down, it sounds like.
Yeah. So if you've got a building delivering heating and cooling, so in the summertime, what we would be looking to do be deliver cooling to the building, and then any of that waste heat, rather than it being going through an evaporative cooler on the roof, wasting enormous amounts of water. We're talking millions of gallons of water just being evaporated from a rooftop building.
Wow.
We would use that heat and heat maybe a hot water for the residents, or a swimming pool or something. So some of the district energy solutions that we see, especially in the New York area, and NYSERDA here in New York is a fantastic organization, and there's some great incentives that are now offering district energy feasibility studies, where they will pay the full feasibility, and some great exciting opportunities to be had here in New York.
That's awesome. And now, so when we talk about energy foundation solutions, like how are those different from, say, a conventional geothermal solution?
Yeah. Okay. So there are a multitude of solutions. So we can put those geothermal loops into bodies of water. So a lake, we put them into the bottom of a lake. We can put them in horizontally and football playing fields. And we've done that in schools. Very cheap solution. And one of the most predominant solutions that we see in New York is where you come in and you drill purpose-made drill boreholes down to 500 feet, 8 to 10 inch in diameter, creates a lot of spoil. But the energy foundation solution is one where we would simply work alongside the foundation contractor and attach the geothermal loops to the building foundation reinforcement and install it with the foundations. Very, very, very rarely have we ever gone back and said, well, actually, the piles are not deep enough. And they need to be deeper. So we would just use the structural length of the pile. I should caveat that. I mean, I would say a good depth of pile is probably somewhere around 60 to 80 feet.
Okay.
Anything shorter than that, it's probably not worth looking at an energy foundation solution, depending on what you're wanting to heat and cool.
Okay. And what diameter? What diameter elements too small?
Yeah, so the smallest I've done is probably a 6 to 8 inch diameter pile.
It's pretty small.
One single loop. But then the larger the diameter, then we start to add in more loops. So the project I'm currently working on here in Manhattan, the 24 and 36 inch piles, and we're putting 3 geothermal loops in each. So 6 pipes, all connected in series. Yeah, so the larger the diameter of the pile, the more loops we would put in.
Got it. And that's connected directly to like the internal steel cage, and it's lower down, or do you?
Yeah. So
how do you get it in there?
And again, I've done about close to 60 energy foundation projects, and one of the things geotechnical engineers will know is there's a multitude of foundation solutions.
Exactly.
And I've probably put a geothermal loop on almost, I think every geotechnical foundation solution. So from precast piles, driven cast in situ, and I apologize because I'm using probably English terms.
Right.
I know there's difference, and there's a guy called Tracy Bretman who I'm sure a lot of you guys will know. He actually wrote me out a list of sort of continuous flight auger is auger displaced piles or something.
Yeah.
Yeah,
crib sheets. This is what it's called over here. Depending on what side of the pond you're on, right?
Yeah. It's a bit like inches and centimeters in the UK. I'm constantly having to I regularly get it wrong, so apologies. And
no worries.
But yeah, so slurry walls, we put geothermal loops into those in station boxes in the UK. Large diameter, right the way up to probably 8 to 9 feet in diameter.
Wow.
As well. Displacement piles over in California. Great solution. The solution there was we put 3,000 energy foundations in over there.
Wow.
The original solution there was to drill boreholes, and they had highly contaminated ground.
Okay.
And the concern was they were going to drag contamination down into lower aquifers. Whereas the displacement pile solution, as you guys I'm sure know, as you're drilling down, the material is being forced into the ground around the pile and the auger tools. The grout is then pumped in as the augers are removed, and then you've got a single bar that was being installed down to 120 feet on 3,000 piles. Fantastic project that I was involved with in 2017. Big campus facility that was going to deliver all the heating and pretty much all the heating and cooling to the building. But yeah, and again, it just shows the benefits of this type of solution. You've then not got another technique on site. You've got not got another set of equipment generating piles and piles of drilling material, slurry. And it's simple. You get the coordination right on these on an energy foundation solution, and there should be no impact on the construction schedule. And that's one of the biggest things that we see. So yeah, it's a pretty straightforward solution.
That's awesome. Do you find yourself putting them in the mat as well? Like if you had a thickened mat or a thickened raft, does it make sense to have them horizontal?
So I know in Europe they do a lot of that, but when in our analysis we tend to find that it actually doesn't it doesn't provide much in the way of additional benefit. And if you do, I would then be concerned about kind of so you'd be probably heating a room, and in heating the room, the ground below it is then going to get cold. So you've got condensation issues. So you then go add sort of an insulation layer, which could become quite a significant additional cost. And to be honest with you, I've always felt that for the amount of effort you put into the horizontal loops in the raft slab, you probably end up it would be too costly. For the amount you get out of the loops. So what we have done in those situations, we have drilled purpose-made boreholes if there wasn't a foundation solution detailed for that. So yeah.
Okay, that's helpful. So I'm sure there's a listener that's saying, "Wow, we should just do this on every foundation." But what are some of the hurdles that can prevent this from being a solution for every foundation?
So, yeah. So the biggest hurdle we're always being asked, well, what's the payback of this kind of solution? Is one of the hurdles, and the biggest issue we come up against is when this is what it would cost compared to a business as usual type case. And gas costs, in the Midwest are so low that it's difficult to show a payback less than probably 15 years. And I would say that's probably the biggest hurdle we have. The second hurdle is the kind of, the mechanical engineering guys that are driving the solution that are not familiar with this technology. And they've spent their life sort of designing and building gas-fired boilers for heating and rooftop units for cooling, VRF, variable refrigerant flow. So people are very stuck in their ways. And what you see is a developer will go to their tried and tested mechanical engineer, and he will come up with a solution that he knows, and they're very reluctant to change. But what we're seeing now is there's a big drive, especially in New York. I mentioned the NYSERDA incentives for moving towards geothermal solutions. I'm now based in New York myself, purely because I see the NYSERDA incentives, the PON 4614 as it's called, as being an absolute game changer in New York. We've got Local Law 97 coming in New York, which is, if you're using gas-fired boilers by end of 2025, some of these building owners are going to incur some pretty big penalties for CO2. So there's a big shift, and it's not been the easiest thing I've ever done in my life. Trying to sell one of these solutions is a long game, and I would say it's probably an 18-month discussion. I do a lot of business development. That's my role within GI Energy largely, and to go out there and meet people and trying to persuade them, well, look, this is where we need to be going. And the project I'm currently working on with Hines, that 561 Greenwich is an absolutely fantastic project where it's a Langen project. Langen were the guys that sort of got us involved here. 120 feet deep piles, 14-story building, and we're delivering 40% of the building's heating and cooling, which is a massive chunk of heating and cooling. When you combine it with an air source heat pump solution, you've got an all-electric building, and what we're building on this project is the type of building that should be built everywhere. Energy foundation on a city centre site. What else there is no alternative but to look at the foundations and the energy foundation solution as part of a carbon reduction solution.
No, you're right. I mean, the reality is that if you have to drill that deep and you have to put that volume in the ground to support your building, if you can tinker with it a little bit, if you can adjust it just a little bit to take care of the ground couple, it could be a win for everybody, environment and people that are going to be in the building as well. So that's awesome.
Sure.
That's awesome. What do you think? I mean, you were going to say something.
No, it's well, just I was just going to come back to the last hurdle is
Yeah.
the technical and the mechanical
Yes.
disconnect, and it's and certainly here in New York, it's you've got lots of parties doing little bits of the solution. This is a kind of solution that needs one party to then oversee all this being brought together, and that's another hurdle that I see in this type of solution. But we're slowly changing things. NYSERDA, as I said, is a great incentive. I'm seeing there's going to be a big shift, very quick shift now.
So if you're looking at it from a feasibility standpoint, that's early enough in the project to see if it makes sense, if it doesn't make sense, and then making sure that all the right people on the team have bought into this, right?
Yeah.
And so it's not forgotten. You don't want to get to the point where it's time to do foundations and we didn't buy the loops, right? We have to make sure that all parts are looking at this. And now, is there a testing afterwards to see, how well the system has worked after 4, 5, 6 years? How does that work?
So here's the thing, and one of the things that we're doing on the project that I'm working on is we've put a lot of instrumentation into 3 piles that's going to monitor the temperature through various levels. But we're also we've got a monitoring device that will be recording what's actually being demanded of the building in terms of heating and cooling. So that energy profile that I mentioned earlier is an absolutely crucial part of the design of the geothermal solution. And what we and I've listened to many developers that said, oh well, the energy model's never right. So I'm thinking, well, you're not obviously using the right kind of people. And it's kind of like a get out of jail free card.
Yeah.
But it fundamentally it's the holy grail of what we do. And so the Greenwich project, what we're looking at doing is we're going to develop we'll end up with an energy profile throughout the year for heating and cooling. And what that will enable us to then do is to then look at, well, can we deliver more heating? Can we deliver more cooling from the foundations? But importantly, what that control system will be doing, we'll be looking at the air temperature and the ground temperature and what's going on in the ground loop. And when the air temperature is a certain point, it could be slightly cooler than the ground. Maybe this morning in New York, it's been a very hot day. So they'll be looking for predominantly cooling at this time of the year. But it could be that the air temperature first thing in the morning is cooler than the ground, which means that an air source heat pump solution would be doing less work. So that means the efficiency of the air source heat pump will be more efficient than the ground source heat pump. So we can then send a signal to, okay, let's use the air source heat pump. And then as the air temperature is rising, and it goes beyond the ground temperature, we can then send a signal to the heat pumps to then change to using the ground and things like that. So once we have that energy model, we can then start playing around with the ground and the foundations and making them work harder. So it could be that, in the winter time, we can deliver more heating, we cool the ground down, such that come the summertime, we've got a much cooler ground and we can then deliver a lot more heat, a lot more cooling. And that's the kind of where we're going with this kind of solution.
That's awesome. So again, with the fridge analogy, right? You're just changing the knobs on the fridge, right? You have a very smart building there.
A very smart building, and the controls are pre-programmed. So the idea is that maybe after 18 months we go back, we then check what we originally designed, and then okay, this is the actual energy model that we're actually delivering. This is the true picture. So we're comparing that against what was designed. And then also at the performance of the ground loop, we can then start playing around with it. It's a bit like a graphic equalizer. I mean, I could never understand on my stereo.
Yeah.
When I was a kid, all these levers.
Yeah.
You can put algorithms in your control box that work out what's the most energy efficient way of delivering heating and cooling at a precise moment in time. And that is crucial to where we're going here. And most of these buildings will be, they shouldn't need a lot of management once you've got that fixed.
Yeah.
And what we'll be able to do is we'll be able to dial into that system remotely and see how it's performing over time. And maybe after the 2 years are up, we've got a good profile of what's going on, and we can start to make sure it's working as it was designed. And the beauty of that control system is that we can then look at outperforming what we thought in terms of CO2 savings, energy savings for the building owner ultimately, is what we're trying to achieve. And that's
nice.
So those are the kind of the measures that we're putting in place to check what we do.
Okay. And then for the geotechnical engineer that's listening, from a design standpoint, is there anything the engineer has to be thinking about for the long-term integrity of the pile, reduction in capacity? I mean, we're talking about small loops in the pile, so there shouldn't be, but is there anything they need to be worried about if you introduce your loops into their pile?
So interesting, good comment, because one of the first things when we tried to raise the profile of this back in 2003-4, a lot of geotechnical guys were saying, well, what happens, are you going to freeze the ground and all that kind of stuff? And there were horror stories of geothermal loops, boreholes, and especially horizontal loops, where there were playing fields, and they became ice skating rinks because they were freezing up. That is a sign that a system is not working. That is a sign the system has failed.
Okay.
So going back to the control system, ultimately we don't want to do that. And as a result, I very luckily, with going back to the cementation Skanska days, we did a great study. We got Cambridge University involved, and the cementation team, and we did I think it was a 4 to 6 week. We load tested a pile. We put geothermal loops in it. We had fiber optic cables in there from Cambridge University, and we monitored what happened to the pile over time. We actually tried to freeze the pile, but we couldn't actually get the ground below freezing after probably 3 or 4 weeks of really trying to freeze the ground. But you get the contraction, you get the expansion, and what we found was the pile shifted by, I think, if I remember rightly, 5 or 6 millimeters.
Okay.
And again, I apologize for being metric.
It's all right.
And then when we then switched the heat pump to heat mode, and what we saw was the expansion, and the 5 mil of settlement became 3 millimeters of settlement. Okay. And so we culminated in demonstrating through all the strain gauges that we put into this pile that there was nothing untoward, and putting geothermal loops into the foundations shouldn't have any detrimental effect. What you don't want to be doing is putting in too many loops. And one of the things that we would say is that the loop goes down, it comes up, and as long as you've got probably a 1.5 foot between the flow and the return, generally then you've got adequate space around the circumference of the pile for an effective geothermal solution. And again, that's kind of going back to the diameter of the pile. As the pile get bigger,
yep,
we would add loops for sure. But and I think the only thing that you might want to check is the compressive strength of the concrete's not affected by the reduction in loops. I think that was the only check that we would suggest.
Okay.
But again, coming back to the controls, looking at the whole system holistically, and not leaving the mechanical engineer just to run your energy foundations is a critical piece, and having that control strategy that's monitoring what's going on, and ensuring that you're not overheating and not overcooling. What will happen is the heat pumps themselves will default before the system, the ground loop fails. So.
Excellent. All right, you put your future glasses on and look forward. What does the future hold for geotechnical engineering?
So one of the things I've come across is a lot of really exciting new materials, phase change materials, polymers, So I think there's going to be a lot of developments. Well, there already is a lot of development in on that side. I kind of like the idea of a lot of some of the grout is recycled materials. Just walking around site today, seeing the amounts of materials, I'm thinking, well, you know, a lot of plastics, maybe we should be using a lot of more of that, just to, you know, rather than going into landfill sites, there's potentially the opportunity to reuse that. But one of the things that, and again, going back to my cementation days, was that one of the guys, especially in London, we're seeing third, fourth generation buildings going up in the city of London. And one of the things that was becoming an increasing problem was that pile's in the way, and you're getting more piles in the way. So I don't know whether Langens have that. I've come across that.
Certainly.
Some of the city sites, you know, you've got third, fourth generation. Okay, you've gone from timber piles, which are you can extract easy enough, but then all of a sudden you're getting these big concrete piles that are not, they're in the wrong place, and it's very, very expensive to core those out. Yeah. So Rab Fernie from Cementation was a key driver of reusing building foundations. And through our QA, QC kind of processes these days, there should be no reason why, you know, some of these foundations shouldn't be reused. I think there's an insurance aspect of it. Was the biggest hurdle, but I think, you know, if you keep good records, concrete details and things like that. So I think, you know, we're going to see a lot of that being considered for sure. And also, you know, if you've got geothermal loops in it, there's absolutely no reason why you shouldn't be able to reconnect those loops for the next generation of building. You know, we did a study with Arups. We put geothermal loops in the Crossrail stations in London, and one of the things we had to demonstrate was the life, the design life was 150 years. So we demonstrated with Arups that the geothermal loops would be certainly around for longer than 150 years. So again, the reuse of foundations is something certainly in city centre sites like New York, where you're starting to get third, fourth generation of buildings. You know, some would say, well, that doesn't make good economic sense to me as a foundation contractor. But, you know, to a developer, I think it's going to become quite important. As we see, you know, buildings go up. Hong Kong, you know, buildings were going up and buildings were being demolished within sort of less than 20 years.
Yeah, you're right.
And in fact, you know, one of the things that upset me most recently was somebody phoned me and said, oh, well, there was a building I worked on back in probably 1992 or something.
Okay.
Says you were the project manager on that job. And I said, yeah, I was. He said, well, it's being demolished and they want to know, they're looking for the foundation details. I'm thinking, I'm really starting to feel old because, you know, that is 25 years old. And that was an amazing project. It was a project in London where we had to put a secant wall, pile wall all the way around a public house. Because they thought Sir Christopher Wren had designed the arches in the basement of this building. And we had to excavate all the way around the perimeter of this building. Okay. The building ended up being in the middle of about, I think we excavated probably 30 feet around it. Oh, and we had anchor bars going across, and it was one of those projects that was a big headache, but we achieved it. And you know, I went back probably 5 or 6 years later and had a drink in this pub, which was rather unassuming. Why did they bother? You know? But, so yeah, you know, they're now demolishing projects I was working on. That makes me feel.
I've not seen that yet, but with time, I guess that could happen.
Yeah. So it comes back to the reuse of foundations piece, and that was. You know, that's what they were wanting to do, and they said, you know, my name was I was the project manager on it, and did I have the records? I didn't keep things like that. This is in the days before laptops. So
Yeah, it's a hard copy in somebody's desk somewhere.
yeah, the QA/QC, it should be in a box somewhere.
It
But
should be. It should be. Pull it up in the archive, right? That's great. Well, this is a good point to stop, and we're going to come back in just a minute and close this one out with Tony and our career factor of safety in segment. Stick around. Welcome back. It's time for our career factor of safety in segment. In geotechnical engineering, just like many disciplines of engineering, it's important to incorporate a factor of safety into your design. But what about incorporating a factor of safety into your career? Today, of course, we're speaking with Tony Amos. Tony, you've had an already very successful career. When you look back at your career, what's one thing you've implemented in your career to give yourself a factor of safety?
so I thought about this at length. I think it's being diverse, being open-minded. I was never a designer. I was never an estimator. My focus, my role was a project manager, and my skill was bringing all those people together. And I think it's being open to new ideas, having enough skills. I mean, I spent time in estimating, I spent time in the design, so I had a good all-round sort of overview of what I was doing. So it's being having the ability to find something you enjoy, but having a backup plan to do something else. So I'd be quite happy to be an estimator, but I think I'd get bored of sitting at a desk all the time. I'm the kind of person that likes to be on the move, different scenery all the time. One of the things I really enjoyed about my early career was the fact that I was on site for probably maybe a couple of months, and then I was on to another site. And what I really liked about it was I saw a lot of the UK that I'd never visited before. But yeah, I'm sort of estimating, bit of design, and my knowledge grew. And I think I mentioned some of the kind of inspirational characters in my life. There's people like Ken Fleming, Rab Fernie, David Greenwood. At the time, I didn't realize that what they were as individuals in the foundation, the geotechnical world. But they were their can-do attitude. And when there was a problem, we had a problem with on the project, you could go and talk to those guys, and they always had a good answer, a good solution behind you. So again, it's kind of being open-minded, and just being open-minded, broad-minded, whatever you want to say. And I think that for me has been quite an important sort of way of life.
That's great. That's great. Especially, what we do as geotechnical engineers, you're kind of dealing with the unknown. So that's a great nugget of truth there. Well, Tony, thank you so much for coming on the show, and thank you for sharing the insights that you shared. A lot of information here to unpack and good advice to our listeners. Now, if a listener wants to reach out to you, what's the best way for them to find you? Social media, an email? What can you share with us?
I'm on LinkedIn. I'm
Okay.
happy to talk to young engineers, mentor. I think mentoring is a great thing to do. Young people today need to be open-minded, and I'm very approachable. So yeah, LinkedIn.
Excellent. Well, thank you so much for coming on the show, Tony. This was awesome.
Absolute pleasure. Doing a great job, Jared.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and/or questions. Please feel free to go to geotechnicalengineeringpodcast.com, where you'll find a summary of the key points discussed in today's episode, that being episode 24, as well as links to any of the resources, websites, or books mentioned during this episode. Until next time, we wish you the very best in all your geotechnical engineering endeavors. Peace.